Okay, Bismillahirrahmanirrahim. Assalamualaikum, and let's continue with the next topic on our pre-recorded session for power system analysis. And today we're going to talk about real reactive power and power factor control for synchronous generator. So basically, we want to discuss how are we going to control the two type of power and as well as the power factor on a synchronous generator, because the real and reactive power here basically it must be equal to the generator. Say for you have a generator here, and it will always need to be equal to the load power. Okay, whatever the Q generated by the generator, it must be equal to Q generated Q of the load. Q means reactive power lah. Okay, so the generator cannot control how much P and Q, because P and Q basically depends on how much the user use the electricity. Okay, because you cannot control that what the customer will turn on or turn off any time of the day. All right, so how much power, real power that the consumer wants, and how much the reactive power that the consumer equipment require, that all very dependent on the customer, and the utility or the operation control, the operators of the generator cannot control. But the only thing they can control is the voltage of the generator as well as the speed of the generator and field current and all those things lah. Okay, so you're going to see how's that. Okay, so before that, let's talk a little bit on the concept of infinite bus. Okay, infinite bus. You need to know what is called by infinite bus here. Okay, so to begin with, basically most synchronous machines or most generator, I can say synchronous generator lah. Okay, not synchronous machine, are connected to large interconnected electric power network with multiple generator and large number of loads. So you can see at this picture here, this is just a simplified picture of an interconnected load where you have a few generating station here and here, and this one here and this one here. This is only 4, but basically in Malaysia there are more than 4. Okay, and then you have all these transmission lines connected to all the different loads scattered everywhere around the large geographical area, and then this generating station will serve all this load, all this 1, 2, 3, 4, 5 load. Okay, so depending on which generator, because the load basically cannot know where their power come from. It can come from this power station, or maybe come from this power station, and it's all we're going to talk about load flow later on. Okay, so there are two very important characteristics that interconnected power system require at the connection point. Okay, when I say a connection point, is that okay? This is a connection point, one connection point here, and perhaps 2 connection points. It's basically the interface or the connection between the generator and the large power system. Okay, so say you have a generator here. Okay, a generator, and you are connected to a bus that generate the electric the field voltage, the armature voltage, and then you have the synchronous reactance and the current flow through, and this is the bus where the connection point is. Okay, and at this connection point here, connection point or the bus here, it's important to maintain 2 parameters. Okay, as I said before, the system voltage must both magnitude and angle must be constant, as well as the system frequency must also be constant. Okay, in Malaysia is 50 hertz, in case in some other part of the world it perhaps 60 hertz. Right. Okay, that you have always to remember that for any power system, these are the 2 most important parameters that the generator at the point must maintain. Otherwise, the system will collapse and the power system will not work, will not function, or maybe the generator need to be taken out. Maybe there's some problem, because if it cannot maintain the voltage and frequency, then it have to be done something lah. Okay, so if you have a power system which has these 2 criteria at the connection between generator and the large system, then we call it an infinite bus or infinite connection point. Okay, so in definition is, okay, when a generator is connected to an infinite bus, the terminal voltage VT of the generator, which is voltage here, okay, VT of the generator, will not be altered by any change in the excitation of the generator, and no frequency change will occur regardless of any change in the prime mover, okay, input of this generator, or how much reactive power is drawn from the supply, because P and Q will flow, P will flow this much from generator to the last return. It doesn't matter whether the P increase or increase, even Q or increase or increase, right? So the voltage here must always be maintained. It's always maintained at the same value, and the frequency also maintained. Then we call that this point here as infinite bus. Okay, so always remember that for infinite bus, same voltage, same frequency. That's all, guys. Okay. All right. So let me tell you a little bit on theory because of that. Okay. So so basically, a synchronous machine, when connected to infinite bus, basically there are two parameters. I said before, in order to maintain same voltage or same frequency, the generator need to maintain the same speed. Okay, because speed is very related to frequency. Right. So at the voltage terminal, okay, so VT here is basically the generator voltage need to be maintained constant, because these are the two parameters, the speed as well as the terminal voltage, or I can say the phase voltage, need to be maintained. So we can control these two value here. Okay. So there are basically two most important controllable variable in the generator. Okay, so you can control, as I said, you can control the field current. Okay, because the field current in the field winding will control the generator voltage E or E phase, and this can control the variable amount of supply or absorbed reactive power Q. So if you control the voltage, you can control the Q. Okay, the reactive power. And then secondly, if you can control the mechanical torque, okay, of the generator shaft, you can control the supply of real power P. Okay, and that is just the theory first. Okay, so we're going to talk about more on how we model that in terms of mathematical equation. So basically, when the generator can control P and Q, the generator can control the power factor of the system. All right. It is not like controlling or try to reduce power factor. It's basically how the generator react to the different power factor of the load. Okay. So now let's analyze how the generator control the reactive and real power supply. Basically how it control or react to the power factor of the system. Okay. So reactive power control. Let's talk about reactive power control first. Okay. So a synchronous machine is connected to an infinite bus as shown here. Okay, you have a generator here. Okay, connected to an infinite bus. This is an infinite bus. Is connected to the large power system. Okay, the load and connected generator and all of that. Okay, and then we assume that, okay, for the time being, this generator is a round rotor type of generator. Okay, because for a salient pole, and then the analysis will be a little bit different. Okay. And then secondly, we assume that they will neglect the armature resistance here. So basically, there's no resistance. Because as I said, as we have discussed before, the armature resistance is typically very, very small compared to the synchronous reactance, so we can ignore it. Okay. And very importantly, the generator, we assume that it is delivering a constant real power. Okay, a constant real power. Basically at that time, certain time, the P is fixed. Okay, so basically when we say P is fixed, this says that we are going to see how the generator will be controlled in terms of when Q increase or Q decrease. Okay, so we fix the real power, but we're going to see how the Q will vary in terms of the value lah. Okay, and then finally we assume that the terminal voltage is to be desired to be constant, and the frequency is desired to be constant. Okay, so as you can see from basic formula that you have learned before, that the apparent power or the complex power is equal P plus JQ. Okay, it's a complex value. It's basically a phasor. Okay, and it's also equal to V, the voltage of the terminal here, multiplied by the current, the armature current conjugate. Okay, this is the basic power formula. And then we can split it into two, which is VTIA cosine theta plus J sine theta. Okay, so we can split it into two. So from here we can derive the formula for the real power. This is a per phase. This is basically per phase. Per phase. Okay, so for the per phase, as I said, single phase or per phase, it's the same thing. So the per phase real negative power delivered or absorbed. Okay, because the real power always been delivered. The generator cannot absorb real power unless it's a reverse power condition, but we're not going to discuss that. Okay, so for the real power delivered for per phase, it depends on the value of the terminal voltage multiplied by the value, the magnitude of the current multiplied by the cosine theta. What is cosine theta? Is the cosine theta power factor. Okay, this is the theta power factor. Okay, for the reactive power is similar. It's the same as voltage multiplied by current, but multiplied by the sine of the theta power factor. Okay, this is the power factor angle. Okay, so from this power factor triangle that I have shown you before, you can see that if the Q is greater than 0, okay, is Q. So if you want a Q here is greater than 0, then IA sine theta must also be greater than 0, because V here is always greater than 0. You cannot have a negative voltage here, right? So here IA sine theta will always be greater than 0. So basically, if you have a Q greater than 0, then you have a lagging power factor. And what lagging power factor means, when I told you before that it tells you that the generator is supplying Q to the load. Okay, the Q is basically being exported outside. So in of course the P is always out. Okay, for lagging. For lagging. Okay, the Q is being exported from the generator to the load. Okay, this is the load. Okay. And vice versa, if you have Q less than 0, so of course for this equation, for Q less than 0, then you have IA sine theta will be less than 0, and because of that you have a leading power factor. Okay, so in order for IA is positive, but sine theta means the angle will be on this side of the complex plane lah. Okay, then when you have leading power factor, basically the generator will be absorbing Q, so basically the Q will flow this way. Okay, the Q will flow this way for the leading power factor. Okay, but the P will always be flowing outside, exporting to the because here you can see that the P is always being constant, right? No matter what, no matter the Q is positive or negative. Okay, of course the apparent power will change, right? The value of our apparent power or complex power will change, but you can see that in this vector we are maintaining the real power to be exactly the same value, no matter the power factor is lagging or leading. Okay. Okay, now let's pay very close attention to this explanation. So, all right, remember that our objective is for the voltage, phase voltage or the terminal voltage to be constant. Okay, so remember the relationship, the phasor diagram relationship for lagging power factor. Okay, is okay. If I reverse V and E, so we have this equation here, the V phase here equal to the EMF voltage minus JXIA, right? Okay, remember these two parameters are phases. Okay, so this is what we're going to have it to be constant. All right. So E has a angle of delta, V always angle 0, is always constant. Okay, and IA has the angle of theta power factor. All right. So now let's take a look at this equation here. Okay, so if you want to maintain the voltage at the phase voltage equal to 0, at least at a certain value is 0, meaning that if you this value, the induced voltage phasor minus this voltage phasor must always be equal to this. Okay, no matter what. Okay, let's take a look at the simple phasor example, right? For example, kan, macam ni. If you have, let's say, you want to maintain the phasor diagram like this, you see? So this, let's take this as a A phasor diagram. You want to maintain this A to be fixed. Okay, because phasor addition or multiplication or subtraction is not like 1 plus 2 equals to 3. Okay, so if you want to maintain a fixed, then you can have a different type of addition. For example, you can add these two vector plus these two vector will have a value, right? Or you can have this vector here plus this vector, you can still have the value of a. Or you can have this vector here plus this vector here, and you still have the value, the resultant is a, right? So you can have two vector multiply or subtract, and then you will get the same a vector. All right, so basically if you have a slight change in this vector, then this vector need to adjust, so that if you subtract these two together, we'll always get the same vector of voltage at the angle of 0. Okay, you know what I mean? Okay, okay. So let's clear this slide. Okay. Okay. So basically, if you have a lagging power factor, okay. All right. Let's take a look at this phasor again. This is the same phasor diagram that I've shown you again and again. So let's say, for example, you have a phase angle, a current direction flowing this way at this theta power factor 1, and this is the green vector here is basically the phase vector of the voltage at the phase that you want to maintain it constant. Okay, all right. So if you basically this phasor that you want to maintain, so basically meaning that this E at the angle of 1, the induced voltage, this voltage here, this phasor here, minus this voltage here must equal to this voltage here. So this is one phasor here, okay, for the angle. Okay, because remember that you have this J here. Why is there's a plus 90 degree? Because J here, what is J? J equals to 1 magnitude at the angle of 90 degrees, right? So if you have theta 1, so this is a phasor for IA. This is a phasor for XS for the synchronous reactance. So if you combine the multiply that together, we'll get this, the magnitude of, this is basically the magnitude XS multiplied by the magnitude of current for 1. 1 means that at lagging lah. Okay, 1 means lagging. 1 means lagging. Okay, and then you add the angle together lah. All right. Similarly, like a simple vector addition, vector. Okay, so and then you can see that IA can be projected into IA cosine theta. Remember this P here need to be maintained as constant. So basically, I cosine theta need to be fixed. Okay, it cannot change. You can have IA, for example, at this direction. You can have IA1 at this direction. No matter what, as long as it fall in this direction, then you will have a fixed amount of IA cosine theta, because real power here depend on IA cosine theta. Okay, all right. So and then okay, let's take a look at the second one. Okay, here I'm going to show you also that okay, for the generator voltage E, this is E1. Okay, this is basically, I can say this is E1 here. You can say this is E1. Okay, all right. So if you project them at the y-axis, okay, let's call it the y-axis, and this is the x-axis. Okay, if you project them at the y-axis, then you will have this value here, E sine delta 1. Okay, so let's put it there first. All right, and then let's take a look at the next vector. Okay, so now for a power factor. So if you have a unity power factor, all right, if you want to also maintain the same voltage, okay, all right, so unity power factor looks like this in the yellowish phasor. So you have IA1 shift is in the same direction as the terminal voltage. As you can see, the voltage here V is still maintained constant. Okay, so this is the resultant. I'm sorry guys, this is not plus, this is minus. Please correct me. Okay, so minus JX IA01. So you can see that the unity power factor, you will have this vector here, and as you can see, the current here IA2, or 2 means a unity. Okay, is exactly on the horizontal value lah. So it doesn't have any imaginary value. So it basically is maintained. So it's the same as IA cosine theta. Okay. So and then if you have a voltage here, so E at angle 2, delta 2 minus this vector here, and you will always maintain at the voltage terminal at 0. Okay, so the green vector here is still at 0. Okay, and as you can see, if you project E2 at Y terminal, you will have E sine delta 2. As you can see, this E2 has the same value, right? So it also has the same distance here. Okay, that is the requirement. If not, if E sine here has a different value, then you will not be able to maintain the voltage, the terminal voltage. Okay, and then finally, let's take a look when you have a leading power factor. Okay, in power factor, you still want to maintain the voltage terminal at 0. Okay, let's take a look at the phasor diagram. So for leading power factor, you can see the green vector here for the phasor, for the terminal voltage, for the phase voltage is maintained. It doesn't change. But as you can see, if you change the power factor, okay, let's say from lagging to leading, the I here will flow that on the top here. This is for I3, this is leading, okay, leading. And then for that, because of this equation here, okay, so this is minus, this is minus, this is minus, this is minus, okay. So if you minus these two vector together, okay, it must be in such a way that if you minus together, you will always obtain the same vector for the phase voltage here. Okay, so as you can see, okay, let's maybe a little bit confusing right now, but you just want to understand that there's a pattern here. Okay, so we can conclude that from, if you observe all these three type of set of vector, putting it together in the same plane, you can see that if the power factor system changes, the generator will need to adjust the voltage accordingly, because E here, it depends on the value of the flux, right? And it also depends on the value of field current. If you control the field current, you control the flux, and you control, you can increase or decrease the generated voltage. Okay, so basically the E need to be adjusted so that the voltage remain constant and the real power remain constant. That's what the requirement before, right? You want the P to be constant, okay, so and then the voltage to be constant. So basically E adjusted by changing the DC field current, as I said just now, and DC field current will change the flux, and the flux change will also change the voltage value, the internal voltage here, the E. So if you look at the pattern here of this phasor diagram, you can see that in order for these two criteria to be met, okay, so basically in terms of phasor diagram, this value here, E multiplied by sine theta, must be a constant value. You can see that, okay, all right. And then secondly, if you want to maintain the constant power, the IA, basically the armature current projected on the horizontal axis must also be constant. See, no matter what, this is the phase current IA1, phase current IA2, and phase current IA3. You can see that the tip or the end of the vector here, always fall around this dotted line here. Okay, always on the same horizontal line. Okay, and then if these two criteria, then we can always maintain the phase voltage and the real power to the system. Okay, this is only one of the scenario. We can have many other scenario. For example, you can change the P and all of that. So we could talk about that later on. Okay, all right. So let's talk about. Okay, we're going to continue our next session for active power control in our next video. Okay, all right. We stop for now.